Let me see. Yes, it is there.
Hello everyone, I'm Shashank. I'm a PhD student at the Department of Computer Science, the University of Manchester. And as part of my PhD project, I'm studying the semantics of the language of mathematics. So this talk is about phenomena in the language of mathematics and how we can model some of them. So I'll start the question.
Just for 1 second. You please tell us explicitly, do you allow recording?
Oh, I agree. Okay. So I start with the question. So here we have pairs of sentences, and in the first pair, assume that x and y are integers. So statement x and y are prime entails the statement x is prime. Whereas if I say x and y are prime, it doesn't entail, or the statement x is co-prime is not even something like that. And similarly, if P and Q are sets, then saying P and Q is countable as it entails the sentence P is countable, but the same entailment is not seen if we change countable with equinumerous. So we can ask the question that why does A entail B in 1 and 3, but not in 2 and 4, and how do we model this entailment? And in this talk, I'll be partially answering this question by, I'll answer the first part of the question, that why does A entail B in 1 and 3. So this is how the talk is structured. First, I will mention the linguistic phenomena in question, that what things exactly are we seeing. Then I will explain flexible Boolean semantics, which is an extension of Montague semantics. And flexible Boolean semantics has been used to analyze the linguistic phenomena that will be mentioned in part 1. But I'll also mention what problems occur when we use flexible Boolean semantics off the shelf to analyze sentences from mathematical language. Then Winter has worked on flexible Boolean semantics and plural noun phrases and all the linguistic phenomena that I'll mention, and then we'll see his solution to these problems. But his solution has some other problems that will, and we're going to see those problems as well. And lastly, we'll see a fix in the type system, which can be used to deal with the problems that I show in part 2. So first, we'll go to the linguistic phenomena. All the sentences that we saw in the first slide were of the form x and y are p, where x and y were noun phrases and p was a natural language predicate. And all the sentences that we'll see in this talk will be of the form usually x and y are p or x is p. And we'll see a lot of phenomena in place. So we'll see definite descriptions, which are noun phrases with the definite article the. We'll see coordination of noun phrases like 2 and 3, the integers and rational, that x and y. We'll see the phenomenon of distributive predicates and the distributivity versus collectivity distinction, that some predicates describe individuals when used with a plural subject. Some predicates describe each individual forming the plural subject, like prime and countable, whereas collective predicates usually describe the property of the whole collection itself. And then we also have selectional restrictions come into play, where so selectional restrictions are restrictions that are placed by a predicate on the subject that it can take. For example, saying 2 is a countable set doesn't make sense, because being countable is a property of a set and 2 is not a set. So this notion of 2 is a countable set not making sense can be modeled by studying selectional restrictions of predicate. So these are the things that we'll focus on. And now I will, so to answer this question, I'll now introduce flexible Boolean semantics, which is an extension of Montague semantics. So just a small recap of Montague semantics. So the central idea is that meaning of a sentence is based on the meaning of the individual parts that make up the sentence and how those parts come together to form the whole sentence. And so there's this notion of types that we give to linguistic expressions, and types are given based on what objects do these linguistic expressions correspond to. For example, so there are two basic types, E and T, where E is a type of entities and T is a type of truth values. And then we can make more complex type using a type constructor called arrow. So so here I have not written arrow just for the sake of like clarity. So ET means E arrow T, and it means that it's a function from a set of entities to a set of truth values. And we assign types to linguistic expressions because types play an important role in how those meanings combine together to form the meaning of the whole sentence. So, for example, if we have the sentence 2 is prime, where on the left we have the syntax sentence, then we can assign meaning to each of the individual leaves in this tree. Like we can assign the noun phrase to the noun phrase 2, we can assign its meaning to be the integer 2, and to the adjective prime we can assign its meaning to be the function prime dash prime dash, which takes an entity and maps it to a prime number and not and positive not. And then these meanings can combine with each other to produce the meaning of the whole sentence. So I have taken is to be semantically vacuous. So the meaning of the verb prefix prime is just same as the meaning of the adjective prime. And then the meaning of the sentence to S prime is just the meaning of S prime used as a function, and meaning of 2 as the argument. And because of the type system, because the meanings are in a function argument relation, we can combine the meanings together in a function argument relation to derive the meaning of the whole sentence. So 2 is prime means that is the meaning of 2 is prime is the same as the function prime dash applied to the integer 2. So all in this was Montague semantics. Now Montague semantics has been extended to handle coordination, and coordination. So here I show that we can coordinate linguistic expressions of different categories. For example, we can coordinate two sentences like 2 is prime and 3 is prime. We can coordinate two noun phrases, 2 and 3 are prime. And we can also coordinate adjectives, 2 is prime and even. And the type system that I gave earlier, so noun phrases have the type E, adjectives have type ET, and sentences have type T. So if we want to give a meaning to the coordinator and, we see that and is ambiguous and it has at least 3 meanings. But this ambiguity, there's a way to unify this ambiguity by using Boolean semantics. So in Boolean semantics, we use the Boolean algebraic properties of the domain. So it's based on the fact that almost all the domains that we have when we analyze natural language have a Boolean algebraic structure, and the meaning of the coordinator and is just the meet operation in that specific Boolean algebraic structure. For example, if we have the type T, then the meaning is just a propositional conjunction. And if we have any type, the form sigma T, where sigma is any type, then the meaning is just intersection. And because like sigma, a thing of type sigma T can also be thought of as a set of objects of type sigma. So when we do this, then we can analyze the meaning of the sentence 2 is prime and 3 is prime in the following manner. So here the meaning of and is a propositional conjunction, and the meaning of 2 is prime and even becomes this expression that 2 belongs to a set of all prime things. 2 belong to the intersection of all prime things and even things, and this happens because in this case the meaning of and is intersection, because prime and even are have type ET. So Boolean semantics kind of unifies these different notions of and, but we haven't answered one thing: what happens with noun phrases? So And this is not a straightforward question. This doesn't have a straightforward answer because we do not have we do not have a Boolean algebraic structure on the domain. It's not every time you would have a Boolean algebraic structure on the domain of entity. So Winter in his 2002 book uses the Montague raising operator to list entities to sets of properties held by those entities. He calls them the operator is called Montague raising, and this operator is invoked because there's a type mismatch between the denotations of and the denotations of the noun phrase that it working on. So then the meaning of the noun phrase 2 and 3 just becomes the intersection of the set of properties held by 2 and that held by 3. And using this meaning of the noun phrase 2 and 3, we can analyze the meaning of the sentence 2 and 3 are prime. So 2 and 3 and prime just becomes that the function prime dash belongs the meaning of 2 and 3, which comes down to be the same as, so the meaning of 2 and 3 are prime, it's the same as the meaning of the sentence 2 is prime and 3 is prime. And these flexibility operators were introduced by Party and Ruth in the 83 paper. And we call them flexible operators because they are invoked in the case of a type mismatch, and they change the type of an entity. So they change the type of linguistic expression. So we can think that linguistic expressions have flexible type. There's a flexibility in typing the expressions. So we have seen how noun phrase coordination happens in flexible Boolean semantics. So now we go to sentences such as the integers are countable, where we have sets as where the subject corresponds to sets. And in order to compositionally analyze the meaning of the integers are countable, we need to have a meaning of the plural forming morpheme s, the article da, the common noun integer, and the adjective countable. And link and so the meaning of the, because integer is a common noun, it has usually been analyzed as having the type et, and integer corresponds to the set of all integers. And the meaning of the plural forming morpheme s has been analyzed by Link and Sharvey in the unified analysis of mass and count nouns as the following. So plural morpheme, the morpheme s takes a property and produces a set of all non-empty subsets of that property. So it will be clear if we see integers. So the meaning of integers is just the set of all subsets, the set of all non-empty subsets of integers. And this was also mentioned in although the meaning of s was a bit different. Didn't have the non-empty part. Then the meaning of the plural definite article the has been given by Sharvey as the following. So it takes a set of properties, so P of type et to t, and it produces the unique largest set A which so that P A holds, and this is in the Straussonian tradition. So like if there's no unique largest subset, then we say that it's nonsensical. So if we apply it to the integers, we see that the meaning of this noun phrase the integers becomes the meaning of the applied to integers, which is the largest unique subset of integers, which is just the set z itself. So the meaning of the integers is just the set z, and the integers has the type et. Similarly, the reals, the meaning of the reals becomes the set of real numbers, and it has the type et as well. And this works well, because if we assume that countable has type et to t, because countable is a property of set, then in our system sets have type et, then the meaning of the integers are countable just becomes the function countable applied to z. So, and the meaning of the reals are countable also becomes the function countable prime applied to the set of real numbers. So these sentences are collectively predicted to be true or false in the system. The problem occurs when we do coordination of sets. When we do coordination of the integers and the reals, that's because both have type et, and because and in the type et is interpreted as the intersection operation, the meaning of the integers and the reals becomes the intersection of z and r, which is just z itself. So we lose the meaning of the reals in this process. And then if we have a sentence, the integers and the reals are countable, which is a false sentence because reals are not countable, the meaning is predicted to be the same as the integers are countable, which is a true sentence. So there's some problem going on here. And so the thing to note is that it works very well when we have properties like prime and even. Saying x is prime and even is the same as saying x is prime and x is even, or it's the same as saying that x belongs to the intersection of prime integers and even integers. But with sets, this does not go through. So giving both of them the same type results in some problems. Winter gives a solution to this problem by changing the denotation of the definite article the. So instead of it mapping it to a thing of type a, instead of the integers being a thing of type et, he ensures that the integers is a thing of type et to t by taking the unique largest a with such that pa holds and putting it in a set. So in this case, the meaning of the integers becomes a singleton set containing a set of integers. And then note that we cannot how in previous case we applied the meaning of the integers to the meaning of countable. In this case, we can't do that because both countable and integers have the same type, so they are not in a function argument relation. So we can't just apply one to the other to get the meaning. Then he uses an operator here shown by E. It's called an existential raising operator, and it takes two things of type sigma t and produces true only if they have a non-empty intersection. Otherwise, it results in false. And this operator was also introduced by Barty in a 1986 paper. So with the use of E, one can analyze the meaning of the integers of the countable in the following manner. So one can use the covert operator E to combine the meanings of countable and integers, and because how the meaning of the integers is just a singleton set containing that, we get the meaning of the integers are countable it's a correct prediction that the meaning of the integers are countable is just the function countable prime applied to z. Then in the 2002 text, because of some natural language data, Winters says that type mismatch is not the optimum way to use these covert operators, and it is necessary. And then he says that there are empty syntactic elements which correspond to these. So there are empty syntactic elements which corresponds to these operators, and then they should be used to produce the meaning. Thus, each covert operator has a silent syntactic counterpart, and so the syntactic system given by him, it produces a lot of readings, out of which one of the reading is true. The second reading is true, that you can apply E to the integers and take the intersection. with either reals and countable. It produces the correct sentence, but there are all correct meaning. But there are also other readings that we get. So one of them is reading number 1, which is false for obvious reasons, because it says that there exists a set et which belongs to the empty set which is countable. So the problem here is that the syntactic machinery doesn't log intended readings, and we get like 2-3 different readings. And this is just one of the operators. There are more operators that are introduced, like a choice function operator, a minimum operator, and they produce a bit more readings. So for this sentence, the integers and the reals are countable. There are at least 4 readings, and the readings which are undesirable are not logged by the syntactic process. So this is one of the problems. And we solve this problem by not going to syntax again, or not assuming empty syntactic categories, but using the changing the type system a bit, so that we just again come back to type mismatch, and type mismatch would trigger the use of forward operators. So we change the type system by adding a simple unary constructor, call it S. And so now our types are these. So E, T, S of E, E, T, S, E, T. Also we can have like S of T, which is a type, S of E, T, which is a type. So we have 2 constructors, one unary constructor S and one the arrow constructor, which is a binary constructor. And S of something, so for example, S of E corresponds to a set of entities. That's the way to think about the S constructor. And so the first step, we change the type system, and then we use the new type system to produce the correct readings. So we make sure that the integers and the reals don't have the type ET, but have the type SE, because we want them to correspond to set. So we don't. So we just change the type of the plural forming morpheme. So from earlier it was ET to ET arrow T. Now the second ET is changed by an S of E. And similarly, we changed the type of the definite article the. So instead of ET arrow T to ET, becomes SET to FE. That is, it takes a set of, or a predicate on sets of entities and just produces set. Now, the next step, which is important, is to make sure that there's no Boolean algebraic structure to this SE. Because if we give the Boolean algebraic structure, we go back to the same intersection. So we strip SE of any Boolean algebraic structure. And the last step is to extend the Montague-Raising operator from entities to sets of entities. It can also be extended more to sets of entities and other types. Once you do this, the meaning of the integers and the reals become the set of properties held by the integers, and sorry, the intersection of the set of properties held by reals and the set of properties held by integers. So it's very similar to how the meaning of 2 and 3 was the intersection of the set of properties held by 2 and 3. Kind of the same. And then when we analyze the integers and the also we change the type of countable from, so instead of it being of type ET to T, it is of the type SE to T. So it represents a property of sets. That's why it's of the type SE to T. And then the meaning of the integers and the countable, straightforward, it's the same as the meaning of the integers are countable and the reals are countable. So we did a few things. We changed the type system and just changed the operators a bit, so that we can distinguish between properties and sets in our types, using our types themselves. So this was about distributive predicates. I have not mentioned collective predicates, but there are ways to, in the same setting, there are ways to analyze collective predicates as well. So we saw flexible Boolean semantics. We saw how coordination of sets and coordination of properties differ, and we saw our possible solution to model this by like changing the type system a bit. Now there are some limitations as well. So if I ask anyone here that the sentence, the integers and reals are countable, is it true or false? I think most of us would say it's false, because reals are not countable. But note that this sentence is a bit different from what we saw earlier. There's no the between and the real. So if my syntax, if syntactic structure, if I don't have a good grammar, like if my syntax is not, if I don't have a good grammar to parse the sentence, or I can have ambiguous passes of the sentences where I can take the coordination of integers and reals together and then apply the plural definite article. And if I take that pass and use my proposed system, I would predict it to be true. So this sentence is like it shows a limitation of the system that I proposed here. Yes, and then as any limitation leads to a future work. So there are some things that I'm looking at right now. First is, and all of these are based on Winter's 2002 work. So first is like in 2002 work, he gives a distinction between quantification and predicative NPs and how to characterize them and use them. And then he also gives a different typology of predicates. So instead of collective distributive, he calls them atom and set predicates, and this is based on my Dowdy's paper in 1987. This was also mentioned, like be numerous and surround. This was also mentioned in Liebestop. And then he uses this new typology to integrate generalized quantifier theory into his theory of plurals, which is very nicely written and it's done in a uniform setting. So I'm looking at these three things right now, and once we have this, you'll be able to analyze sentences like 6 has exactly m factors and all primes more than y are.
Question. Welcome.
Yeah, thank you. Can you say something about how this or related frameworks deal with statistical or probabilistic properties? Like if you say something like most integers are not prime, like the most, it's not referring to any single integer or even just the set of integers, but rather to either some asymptotic property or a distribution on them implicitly.
The generalized quantifier theory gives like, so it's not just one theory, it's like a bunch of different theories, and then it gives, like, various people have given different meanings to what we mean by most. Some people say it's just more than half, then you would call most. Some people say okay, it's a fixed, more than 6%. But also if I say most integers are also, there's also this intuition part to it, that if I ask mathematician, okay, what would you say, most integers are prime, they would, most integers are not prime. Yeah, they would most probably say yes, but also like some would ask, okay, what do you mean by most? So what I mean to say is I do not know of how to deal with this specific phenomenon. Yeah, the statistical probabilistic notions, these things, these quantifiers.
Welcome.
So your capital S operator, is it ever applied to anything else than E?
You can apply it to anything, but it's not used anywhere.
Yeah, okay. Can you see any uses?
So it can be applied to E, it can be applied to S of E itself. Again, like sets of sets.
Okay.
Yeah. So for example, here I said the countable has the type SET, but actually like it's being countable is just the property of sets. So you can, it should be thought of as a polymorph. Its type should be like S of sigma T, where sigma is any type. But I haven't used it anywhere except using S of E or S of E's.
I think what you're just saying is that sets have a separate reality from other individuals in math, which I think all of us would believe. And there's a nice kind of way of actually making that manifest in this thing. I think it's probably very similar to what Philippe was doing with the set of operator. I think it's just whether you put it into the type or into the probably doesn't matter much. I think we should actually keep a watch out of what the other things are that have a separate reality in math. I can think of sequences, and various other things, ellipses and so on, and I think we'll probably need special mechanisms in our grammars for that. So that's a prediction I would make. And I'm interested in actually collecting what I think of as the informal foundation, which is what are the things that have a separate reality and canonically. And I think we should have a list which we all agree on.
I think we have to start accumulating such. For the next edition of the conference, it is actually a symposium. Now, conference to fit it into the symposium of EuroProofNet. Then we start to look into this list and agree on it. So then the next project will use it. It will be very useful to create such a future of the formalization language of this. So some directly to the talk, some more questions. Yes?
Sorry, it's a naive question. I don't know about linguistics, but from a far point of view, you seem to say, okay, we have one solution, and then we find an example where it's not parsed as we want, and then you propose another solution. And is there any way that you can be convinced that your solution will be correct or correct until you find not correct? So the methodology to validate your result is
one of the methodologies is to see like if considering pairs of sentences or a class of sentences which natural language sentences which entail each other, so or one entails the other, then you see, okay, what does our system predict their meaning to be? Then you get two logical formulas. Then you say, okay, does a relation hold between these logical formulas or not? If not, then I might be doing something wrong, because what my task is to predict, okay, this sentence I need to predict it via a theory, but if the logical formulas have no relation between them, the first one does not logically entail, like in the logical system does not entail the other, then somewhere in the process of formalizing I'm going wrong. So that's one of the methodologies to check.
Then probably we try to prepare for the next. Yeah, I don't know whether we risk topics and then we start. Yes, I know. So Michael, do you agree?
yes, I do.
To be recorded?